Now, to solve systems of equations by graphing, it has a lot of limitations. First of all, the solution needs to be easily identifiable. So if it's any kind of fraction value or anything like that, it's going to be almost impossible to identify that accurately by just drawing a sketch. Second, the ordered pair needs to be something close to the origin. Otherwise, we have to sketch a gigantic coordinate plane to find the point of intersection. So it's instead a much better approach for us if we use some algebra techniques to find the place where the two lines intersect without having to draw a graph at all. So the first of those is called substitution. And so this is where we isolate one variable in one of the equations and substitute into the other. So if we look at the first example, we've got y isolated in this first equation. We have y is equal to 2x plus 1. So that means anywhere where I see a y, I can replace it with that expression involving x. And so that's exactly what I'm going to do. I'm going to substitute that into this second equation. So this bottom equation will now be x plus, and then in place of y, I'm going to put that 2x plus 1, and then equals 7. So the only thing that has changed is the y has been replaced with that expression 2x plus 1 from the first equation. So now what we've done is we've gone from a system of two equations and two variables down to one equation with only one variable. And so we can solve this equation and find the x-coordinate of the intersection of these two lines. So the parentheses here mean nothing, so I'm just going to gather x and 2x to make 3x plus 1 equals 7. I'm going to subtract 1 from both sides to get 3x equals 6. And then finally divide both sides by 3, and we'll get x equals 2. But remember, that's only half of our answer. We still have to find the y-coordinate of the intersection point. And so for that, in this case, it's probably easy to plug into either, just as easy to plug into either of these equations. But the nice thing about the top one is the y is already isolated. So we're going to just go y equals 2 times 2 plus 1. And so 2 times 2 is 4, plus 1 is 5. So we get the y-coordinate of our intersection point is 5. So together, 2, 5 is the place where if we had graphed it, these two lines would intersect. In the second example, we don't have one of the variables already isolated in advance for us. So we need to be a little bit strategic about which variable we decide is going to be the easiest to isolate, get that one by itself, and then use substitution. So in this case, I definitely don't want to do anything in this bottom equation, because to isolate the x, I'm going to have to divide everything by 5, which isn't going to leave me with fractions. To isolate the y, I'm going to have to divide everything by -4. Again, same problem. Instead, if I go to the top here and I go to isolate that x in the first equation, I'm eventually going to have to divide everything by 2, but I can see it will divide evenly into all the other pieces, which will be the path of least resistance to getting a variable isolated and then having an easier time of substituting it into the other equation. So that's what I'm going to do. So I'm going to start off here with 2x plus 4y equals 2, that top equation. I'm going to subtract 4y from both sides. So then I've got 2x equals -4y plus 2. And so now I'll just divide everything by 2. So we get x equals, and then we get -2y, and then plus 1. And so now this is what I'm going to substitute into my bottom equation. And so I'll do that over here. So I'll have 5, and then in place of x, I'm going to put that -2y plus 1 minus 4y equals -23. So now I've got a little distributing work to do. 5 times -2y is -10y plus 5 minus 4y equals -23. If I gather my like terms on the left here, I'm getting -14y. Then I'm going to go ahead and subtract this 5 over to the other side in the interest of saving a little time. So we get -28 over there on the other side. So I'm going to divide both sides by -14, and so I get y equals 2. But again, remember, that's only half of our answer. I still need to find the other half, but I'm going to find that other half of my answer by using the equation where I already have the x isolated. So I've got x equals -2 times 2 plus 1. So -2 times 2 is -4, plus 1 is -3. So my ordered pair for this one is going to be -3 for x and +2 for y. So if we had drawn a graph, this is the place where these two lines would intersect. Clearing some space for the last one here, we again have the good fortune of having one of our variables isolated. In fact, it's isolated both times. So y equals x cubed plus 3x squared plus 2x in the top equation, y equals -x in the bottom equation. So what I'm going to do is I'm going to take that -x and replace y with it up in that top equation. So we now have -x equals x cubed plus 3x squared plus 2x. This is clearly not a linear equation, but the technique still applies. So I've got the equation down to just one variable, so I'm going to pile up everything on one side and set it equal to 0 so I can see if I can try to do some factoring here. So I'm going to add x to both sides. So I get 0 equals x cubed plus 3x squared plus 3x. Now I'm going to factor out an x. So I've got x times x squared plus 3x plus 3. And so now I need to try to factor this expression right here. So unfortunately I can't. There's no two numbers that multiply to make 3 and add to make 3. So I'm going to have to use the quadratic formula to try to solve. I am going to get one answer out of this guy right here. It's going to be x equals 0. So that's going to be one of my answers. But now to find the rest, we're going to need to go with x equals -b. So -3 plus or minus the square root of b squared. So 3 squared is 9 minus 4 times a times c. So 4 times 1 times 3. So 4 times 1 times 3. And if we pause right there, we can see this is going to equal 12. 9 minus 12 is going to be a -3, which means I'm not going to get any real answers out of this part of the expression. So I can go ahead and stop right there and just ignore that. And so the only part of the solution here that is going to yield an intersection point on the graph is going to be at x equals 0. And so now I just need to take that and plug it into either of the two equations, which hopefully we very quickly see means y is also going to equal 0. So the only place that these two graphs, this polynomial function, this s-curve, and then this diagonal line y equals -x are going to intersect is going to be at the origin.